Okay, so for this last section of Module 5, we're looking at theoretical probability of multiple independent events. So the key word here is independent, okay? And I would like you to remember that. Two events, or two, like we talked about last time, like flipping heads or tails, two events are considered independent. So they're independent events if the result of the one event does not, okay, so does not depend on the result of the other event. This is really important. So time is probably the best from a scientific perspective. If you ever are looking at science, time is the most commonly talked about independent event. Time passes no matter what. So time is often used on the x-axis, and we're not doing graphing right now, so I won't make you do any kind of graphing. I don't want to spook you with that, but time is always on the x-axis because it's independent. Okay. Usually doesn't matter what you're doing in your experiment, but time is not changed by whatever you do. So a common example of this is the tossing of two coins. And this is because the outcome of the first toss, so whatever happens in the first toss, does not affect what's going to happen in the second toss. So just because you flip a heads the first time doesn't mean you won't get a heads the second time, and it doesn't mean you will get a heads the second time. But the two events are independent. Okay? Now we're going to look at two different ways we can figure out independent probability or independent events. But first, let me just give you an example. So compared to this, if we talk about a dependent event, that would be something like if you take a card out of a deck and then you don't put it back and then you pull out another card, pulling out the first card is going to affect which card you pull out second, right? So for instance, if you pull out, let's say, a heart the first time, pull out a heart for the first card, there's going to be one less heart in the deck if you don't put it back in when you pull out the next card. So your probability of pulling out a heart the second time has gone down, and that's because those are dependent events, okay? So just, this is a bit of a weird concept when you first hear about it, but try and get your head around that. But we are just looking at independent events where whatever happens in the first event does not affect what happens in the second event, okay? So if we're going to find the probability of independent events, we can use a couple different methods. The first is called a tree diagram, okay? And to do a tree diagram, you're going to list all of the possible outcomes, so all possible outcomes of the first event, and then for each outcome, so for each of the first event outcomes, you're going to list all the possible outcomes of the second event. This sounds super weird, but I promise you when I do an example, it's going to make more sense, okay? So if we're thinking about a coin toss, that we're flipping twice, so two coin tosses. The first time we flip a coin, we can get heads or tails, and the second time we flip a coin, we can also get heads or tails, okay? So if we did a tree diagram, we're going to list the outcomes of the first coin toss, and then this is going to be your first branch of the tree. And then for the first outcomes, you're going to list all of the outcomes of the second coin toss, and this is going to be the second branch of the tree. Again, this sounds very strange if I'm not doing it in real life, and I will do it in real life, and it'll make more sense. Another way we can do this is by making a table, okay? And I will ask you to do both. You will probably find one that you prefer, and that's totally fine. But please learn kind of how, or try and get a handle on how to do both, because they can both be really helpful. I find sometimes with a tree diagram, you need a lot of room, and and it can't always fit, or it's hard to visualize properly, in which case a table makes a bit more sense. And now for a table, this is kind of like a Punnett square, and I don't know if you've done Science 10, you know what I'm talking about, and you're probably groaning and thinking, oh no, I've never thought I'd have to do a Punnett square again. It's got nothing to do with genetics when we're talking about probability. Well, actually, genetics is all probability. In this case, we're not going to look at genetics though. So we're not looking at genes, and don't worry about that, like homozygous, heterozygous, nothing like that. But it's just the setup for a table is the same as a Punnett square. And so when we're doing a table, you're going to list all of the outcomes along the top row as the heading for your columns. And then you're going to list all the outcomes for the second toss as the headings for the rows. Okay, so outcomes of the first toss are the headings of the columns. Outcomes from the second toss are the headings for the rows. And really the main way, it's like a Punnett square, is that you then fill in the table the same way you would with a Punnett square. Okay? Oh, this is actually kind of a bit. Maybe I'll make that a bit better. Okay. Mostly it's this part right here, filling in the table. But for this example, I'm going to actually do both for you, so you can see what they both look like. Okay? All right. So we are doing a 2-coin toss, right? And I'm going to just rewrite this here. So 2-coin toss. And I'm going to do, oh man, that's, sometimes my writing is so bad with this tablet. Let me try one more time. 2-coin toss. Okay, so I'm going to do on this side, I'm going to do the tree diagram, okay? And on this side, I'm going to do the table, and I'm going to show you each. So for the tree diagram, the first thing that we're supposed to do is list the outcome of the first toss. So when we do the first toss, and I do like to label them because it makes it a bit easier for me, there are 2 outcomes, right? We're flipping a coin. We can have heads or tails. So this is our first, and I kind of like to give them branches. So we can have heads or tails for the first toss. And then for our second toss, it's the same coin, so we can also have heads or tails. But remember, we have to list the outcomes of the second event for each of the first events. So for heads, if we got heads the first time, the second time we could also have heads or tails, right? And if we got tails the first time, the second time we could also get heads or tails. And so our outcomes, when we're looking at this, what you do is you kind of just follow along. So I'm going to choose a bunch of different colors here. So one outcome would be to get a heads and then another heads, right? So that's one option. We can get heads and then heads. A second option would be to get heads and then tails. Okay? So heads and then tails. A third option, we could get tails and then heads, right? Tails and then heads. And our last option, I already kind of used a color like that. Let's use orange. Our last option, oops, and you'll notice that I probably said that we could get heads or tails here. Ooh, and I just saw that. Sorry. Your second toss, you can only get heads or tails, because for our second or fourth and final option here, we could get a tails and then another tails. Sorry for that goof. So right here, I just messed up. Your second toss, you can have heads or tails. I wrote heads and then heads because I wasn't paying attention. First toss, same thing, right though? Heads or tails. So these are our 4 different possible outcomes. Sometimes the order matters. It depends on what the question's asking. It might ask, what is the probability that you get a tails and then a heads? And that's slightly different from what is the probability that you get heads and tails, one of each. Because that can happen 2 different ways to get one of each. But to get a tails and then a heads can only happen one way, okay? Now, if we want to do this as a table, you list the outcomes of the first toss as the headings for columns, right? So our first toss, we can have heads or tails. So these are going to be our headings for the columns. And our second toss, it's going to be right here. We can also have heads or tails. And these are going to be our rows. Now, the part that makes it like a Punnett square is that you bring in, so in fact, what might be helpful is I will change the color here of our second toss, and then I will draw it across in a way that you can see. Okay, so our second toss, you can also get heads or tails. So what you're going to do is you're going to, for all of your rows, you're going to put your heads as a possible outcome. Sorry, we should do the first. I'm sorry, guys. So for your first toss, for all of the columns, we should do the first toss first. I'm getting backwards here right now. For the first toss, you got to fill in heads, right, or tails. And then for the second toss, you fill in horizontally across the rows. So right here, I could have heads. And right here, I could have tails, right? And so you end up with the same 4 options. So these 4 options are the same 4 that you have over here. Okay, just 2 different ways of getting the same answer. This can definitely be easier. I'll show you an example on our second page where this is a lot easier to visualize than this one sometimes. The table is a lot easier to visualize than the tree, but it's up to you, okay? Now, it's asking us to list the outcomes. List the outcomes for the coins tossed together and determine their probabilities. Okay, so now we have to list all of our outcomes, and I kind of already did that. We figured out most of the outcomes, but we realized we could have heads and then heads. We could have heads and then tails. We could have tails and then heads, or we could have tails and then tails, right? So this is 4 outcomes. 4 outcomes total. And that's important because we know that our probability formula says that we're looking for the number of possible outcomes that we want over the total outcomes, okay? So that's always our the formula that we've been using since we did just a single event, number of ways A can occur over total number of outcomes. All right. So number of ways A can occur over total number of outcomes. So let's look. The probability that you get a heads and then a heads. Let's start with that. Okay, that's our first one. If we're looking at the probability of you getting a heads and then another heads in a row, you're going to do the same thing. So how many ways can heads and heads occur? Well, heads and heads only happens once. So once. How many total outcomes do we have? We have 4. So that's pretty straightforward, right? And if we wanted a ratio, it would be 1 to 4. If we wanted a decimal, it would be 0.25. And if we wanted a percentage, it would be 25%. Remembering, oopsies, sorry, that got kind of messed up. It would be 25%. remembering that here we're multiplying by 100 to get to 25%. And to figure out how to get to the decimal, we're doing our numerator divided by our denominator, 1 over 4. Okay? Just a quick reminder from section 5.5. What about the probability of getting 1 heads and 1 tails? Now in this case, I'm going to say it doesn't matter the order. Doesn't matter what order. So the probability of getting 1 heads and 1 tails, oh my goodness. Sorry, my alarm is going off here. I'm just going to shut all of that down. Okay, the probability of getting 1 heads and 1 tails, we actually have 2 different outcomes where we can have that happen, right? We could get a heads and a tails, and then we could get a tails and a heads. And right now I'm saying order doesn't matter. So there's 2 possible ways we could get 1 heads and 1 tails out of 4 total. And remember, we always want to reduce that fraction, so pull out a common factor. Okay, so that's 1/2, which would be 1 to 2, which is 0.5, which is 50%. So there's a 50% chance that we're going to have 1 heads and 1 tails in no particular order. And then the probability of getting a tails and another tails, it's the very same as getting a heads and a heads, right? It's only going to be 1 out of 4 because there's only one way we could get a tails and then a tails. So that is 1 to 4, 4.25, or 25%. Okay. Okay, so moving on from there, we can actually rewrite our formula here. When the outcomes of an experiment are equally likely, sorry, that was supposed to be, oh no, that's a Y. The probability of an event occurring is going to be, again, the number of ways that that event can happen over the total number of possible outcomes, okay? So this time you have to do a little bit of extra work to find the total number of possible outcomes and the number of different ways A can occur. So, draw a tree or table diagram. So we've got a question here that are saying we can do either. I will do both for this question, but if you find one that works good for you, that's okay. Please try and learn how to do both though, all right? So we have a spinner. So it's like spinning the wheel. The pointer is spun once. We'll assume it's perfectly balanced, so there's no, leaning towards red, blue, or green. But you have 3 different color options, right? And I always like to write down my options. So I have red, blue, and green. If someone, oops, red, green, and green. Red, blue, and green. If someone asked me what the probability of, say, getting a yellow was, I could easily be like 0 because there's no yellow on the spinner, right? So it sounds like what we're going to do is we're going to spin it once and record the color, and then we're going to spin it a second time and record the color. Okay? So the first way that I'll do it, is my preferred way for bigger questions like this with more than 2 outcomes. So there's 3 possible outcomes per spin, right? So 3 possible outcomes per spin. Now, we're going to do that, but then we're going to spin it twice. So it's not actually 3 times 2, and this doesn't really matter if this isn't clicking, but you'd actually have to do 3 times 3, right? So we'll look at that. Let's look at the table diagram first, because I like that one better. So for our table, our first spin, we know we have 3 options, and our first spin are going to be the columns. So we can have red, we can have green, or we can have blue, right? Those are our 3 different options. I'm going to try and make this as clean a table as possible. I will do my best. Now for our second spin, And I will remember to change the color early on here. We can also have 3 different options, red, green, or blue, okay? You know what? I don't want that line. I'm so sorry. I'm going to go back to blue. The blue just makes a better table. Okay, I'll fill in my table this way. All right. Oops. Geometric shapes are not my skill. All right. So let's talk about our first spin. Remember, we fill in our columns with that possible outcome. Okay? So green, 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 blue, 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 right? And then for our rows, we're going to do the same thing, except we're going to do it across the row. So red, 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 green, 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 blue, blue, blue. And I only changed the color just so you can see how those 2 different letters, like where they come from, okay? So that's our table diagram, not too shabby. If we're going to do a tree diagram, okay, we're going to do the same thing. So I suggest you give yourself space when you're doing tree diagrams, especially this kind. Like, don't go red, green, blue, because then you have to fit 1, 2, 3, 4, 5, 6, 7, 8, 9. It's too squishy and it's stressful, at least for me it is. Anyway, I'm going to erase that. Let's not do that. So we're going to make it nice and wide so we have lots of room. Red, green, blue. This is our first toss. And then, or sorry, we're not tossing. Our first spin. And then for our second spin, same thing again. So for each outcome, we list all possible outcomes. So for the red, first spin, second spin, we could get red, green, or blue again. Green, first spin, we can get red, green, or blue. And if we got blue the first time, again, we could get red, green, or blue the second time. So as you can see, oh my goodness, it is worth it to spread out the business, okay? And then you have all your different outcomes listed, and you can figure them out just by looking like so that. You just follow it down the tree, right? Doesn't let me highlight on an angle, which I don't like. Anyway, and so on, all right? Now I'm going to erase this because they're actually going to ask for a specific, oh, I'm erasing my lines, but they actually have a specific probability they want us to find. Okay, so in part B, and I'm going to try and keep the tree up as well, it says, find the probability of getting the same colors. Okay, so we're going to go back to our tree diagram or our table, and we're going to find, remember what we're looking for, which is the probability, sorry, I'll write it out like this. Probability of getting the same colors is going to be equal to the number of ways we can get the same color over the total ways or the total outcomes, right? Now, it's easier to visualize. I mean, you can count these. So if we count these squares, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if we were to count at the end, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I always like to check so we know there's 9 outcomes. Okay? But we want the same colors. So we're going to go and look. So we could get red and red. We could get green and green. And we could get blue and blue. Right? So these are our same color combinations. Green and green and blue and blue. Perfect. So the number of different ways we can get the same color, there are 3. And the total number of outcomes, there are 9. So it becomes 3 over 9. And we're going to reduce our fraction, pulling out a common factor to 1 over 3. Okay, so that would be a 1 to 3, and I'm showing you all the different ways. I didn't technically specify here, so you could just answer as a decimal. If I divide that in my calculator, I get 0.33 or 33%. Okay? So the next question asks the probability of getting different colors. So we know, we can kind of figure this out. You could go back and count, or we could know that if 3 are the same color, then 9 minus 3 is going to give us 6, which are the different colors, right? Because that's whatever's left over. Okay, we can't always do that, but in this case, you can. If they said what was the probability of getting red then blue, we couldn't do this, but you can look or you can count. So 6 out of 9, and we're going to pull out a common factor, which is going to be 3 to give us 2 over 3. And that's like a ratio of 2 to 3, which is 0, oops, that's not a 0, 0.6666, so we're going to just do 0.67 because it's on and on and on. We usually keep it to 2 decimal places when we're dealing with probability, or 67%, okay? Awesome. Now, last but not least, Karina and Paolo carry out the experiment 100 times. They find that there are 41 of the same colors and 59 of the different colors. How do the experimental probabilities compare with the theoretical probabilities? Okay, so this is an interesting question. So in the theoretical, that's just what we figured out, right? The theoretical probability is what we just looked at. Theoretical. The theoretical probability for the same color was 0.33 or 33%, right? And the theoretical probability for getting different colors was 0.67 or 67%. Now remember, hopefully you remember what percent means. Percent equals out of 100. And I'm just gonna star that because when we look at our experimental probabilities, I was really kind, and they spun it 100 times. So this is gonna help us, right? So for our experimental probabilities, for the same color, the number of times they got the same color, they got 41 out of 100 spins total, which would be actually 41%. And the number of times in the experiment that they got different colors, they got 59 out of 100, which would have been 59%. Okay? So we could say, if, you know, explain, the most obvious thing to see is that they spun 8 more times than the theoretical probability they got the same color, right? Or you could say 8 less times than theoretical they got a different color. Doesn't really matter how you phrase it, right? Because in real life, or in real life here, 59% versus 67%, which was our theoretical percentage, and for the same color, 41% versus 33%. Okay? Now, there's no way to really explain, you know, how or why that happens, because the whole point of a probability is to give you a expected result. It's not to tell you exactly what's going to happen, and that's what any kind of probability or even statistics, that's what you're striving to do. You're trying to find trends, and you're trying to find what you think is going to happen, and then you can compare it to what actually happens. And this is like 99.99999% of science, is you come up with an idea, you look at other ideas, maybe someone's done an experiment before, maybe based on other experiments that are kind of the same but not exactly the same, you know what should happen, and then you figure out what actually happens. So it's actually very common for theoretical and experimental. They don't always line up, especially when you're dealing with small numbers. But the key with this is that you get that bottom number, this number right here. You want your total, the total number of outcomes. The higher that number is, the closer you're going to get to your experimental, or sorry, to your theoretical probability. So the more times you can do an experiment, or the more times you can flip a coin or spin the wheel, you're going to get closer and closer to theoretical probability. I bet you if I had him spin that wheel 1,000 times or 10,000 times, we'd be looking at way closer to what the theoretical probability is versus the experimental. And that's why, and I'm running out of room, but sample size, and I'm going on a tangent here, and you don't necessarily need to listen to this part, but it is interesting, is so important in science, because you want your sample size or the number of people you're testing on or whatever, you want that to be big, because the smaller your sample size is, the more times you can get issues like this. But the bigger your sample size, if you have like a sample of 1,000 people and you see that you're getting the same result most of the time versus a sample size of 10 people and you're getting the same result most of the time, that 1,000 people means a lot more. It's got more statistical weight. It's more important, especially if you think about things like drug testing maybe. And I'm not talking about being tested for drugs. I mean creating a new drug, they need to test for side effects, right? So if 3 out of 10 people get sick on a new medication, let's say they get terrible nausea and vomiting, that's 30%, right? That's a pretty large percentage. And if you were going to give that drug to, say, 100,000 people, you wouldn't want 30,000 people to get debilitating nausea and vomiting. But you only did that experiment, or you only tested 10 people, which is why they will do, when developing new drugs, they'll actually do multiple rounds of trials of testing, and they'll try and test many, many people. And maybe after they test, let's say 1,000 people, they notice that that 30% goes down to 3%. And then that's not so bad, right? And they realize that with more people, maybe they just had 10 people who were really sensitive to the drug. And I'm going on a huge tangent right now, but I did want to point out theoretical versus experimental probabilities, like why this is such a big deal, and why when you see experiments with a small sample size, so like they'll do this often in the news, you'll see a headline, they'll say, you know, I don't know, let's say it is that new drug, and they'll be like 30% of people who took this drug got violently ill, like why are they making it? And then you'll notice that only 10 people were tested. It's really important to look at a sample size before you believe a scientific study, and or you don't necessarily have to not believe it, but you should be like, I wonder if they've done another study with a bigger sample size to see if this still is the rate of nausea or whatever, right? I'm using medication because I worked in healthcare and I worked in pharmacy for 10 years. So that is what I know. But that small sample size, it should be a bit of a flag for you if you're ever looking at scientific or things that are trying to pass themselves off as scientific, especially in the media. They like to take things, and it's not even the scientist's fault, but they like to take things and run with them and make sensational headlines. And oftentimes you can find things like, they only did an experiment with 5 people, and you're like, oh, that's in a very small print. No wonder that they found this result. Anyway, that's going to be the end of my rant because this is coming up on 35 minutes. So yeah, this is the end of Module 5. Hooray!